Hi everyone, I am Surendran Subramaniam. Today we are going to present the report of the experiment which is titled as Vapor Compression Refrigeration for the subject Thermodynamics and Material Engineering Laboratory. My group members are Ranjit Analalagi V. Rajal, Billy Harbison Robert, Muhammad Irfan bin Ramli, and I myself Surendran Analagi Subramaniam. We are from Group 3 and Section 2. So I'm going to start our presentation with introduction part. Refrigerators are cyclic devices that transfer heat from a lower temperature to a higher temperature. Normally, refrigerators use the fuel called refrigerant R141B, which was used in this experiment. Refrigerant can undergo phase change from liquid to superheated and then back to liquid as it is passes steadily through the various components that comprise the system. The system has four components which are compressor, condenser, thermal expansion and an evaporator. So the objective of this experiment is to determine the coefficient of performance of COP for vapor compression cooling system. To accomplish the objective of the experiment, the value of QH and QL will be determined. Based on the graph that will be plotted later, the relationship between flow rate and temperature and the relationship between condenser flow rate and compressor power will be determined. So that's all from me. Thank you very much.
Assalamualaikum, I'm Muhammad Irfan. So we continue to the theory part. So the cooling system accept the heat from the lower temperature space and heat transfer to high temperature space. It requires work to be supplied to the system as you can see in this figure. Okay. Okay, next we move to the working principle. When the refrigerant come to the compressor as a vapor and compress due to the condenser pressure as shown in this figure, it exits the compressor with a high temperature. Then it cools down and condenses as it moves through the condenser coil, feeding the heat to the environment. After that, it reaches the capillary channel where the throttling effect will cause the pressure and the temperature to drop. The low temperature refrigerant is then pumped into the evaporator where it absorbs heat from the refrigerated space and evaporates. Cycle is considered complete when the refrigerant leaves the evaporator and re-enters the compressor. So we need to find the COP, which is the coefficient of performance, by using the equation COP equals to cooling effect over work. Okay, so now we move to the methodology and procedure. First, we need to open these two valves, which is this one and this one. Okay, next we turn on the water pipe and set the water flow of evaporator to 25 gram per second and flow rate to condenser as a maximum. Okay, next, switch is then turned on. This is the main switch. Okay, this is okay. So the cooling system of the device is left to be stable for an approximate of 10 minutes. After that, the temperature of T1 until T4 was obtained by adjusting the temperature selector switch and obtained from the temperature indicator. So the temperature T1 until T4 we get from the this. This is the temperature indicator. Okay. Okay, next, the pressure of condenser and evaporator was taken from their respective gauge, which is here, this one and this one. Okay, and next, the temperature of T5 and T until T7 was recorded manually, which is we need to read the temperature from the thermometer at here, and at here. Okay, so for the next step is the experiment was repeated by changing the flow rate of water for evaporator and condenser between 30 and 5 gram per second. At least 4 set was done for the experiment. And while we need to terminate the operation, we need to switch off the main switch and then we turn off the water supply pipe after 1 minute. And lastly, we close the valve to the shutdown position.
So I'm going to present on the safety procedure. First, the two valves are open and turn on the water pipe and set the water flow and evaporator and condenser to 30 gram per second. Switch is then turned on. The cooling system of the device is left to be stable for an approximate 10 minutes. Fourth, the temperature of T1 to T4 was obtained by adjusting the temperature. Selector switch and obtained from the temperature indicator. Next, the temperature of condenser and evaporator was taken from their respective gauge. The sixth, the temperature of T5 and T7 was recorded manually. And lastly, the experiment was repeated by changing the flow rate of water for evaporator and condenser between 30 to 10 gram per second, and at least 4 sets was done for the experiment. So this is our picture here doing the experiment, and the result is was done by using Excel, and this is the graph for both rate of heat at evaporator and condenser. So the formula that we use to calculate the rate of heat at evaporator is Q equal to mH, where H is the enthalpy. And so, and with the coefficient of performance, the formula is rate of heat of evaporator divided by rate of heat at condenser minus rate of heat at evaporator. So that's it from me. Thank you.
Hello everyone, I'm Ranjit here. So here I will be presenting about the discussion part. So the first question is to calculate the rate of the heat transfer that occurs in the evaporator and the condenser for the 5 tests run and discuss the results. So first of all, we need to calculate the rate of the heat transfer at evaporator using the formula given, which is QL equals to mH. So the H, which is enthalpy, we can obtain from the steam table, using steam table. So using the data which we obtained from the experiment, for the QL1 we got 58.22 kilowatt and QL2 57.99 kilowatt. For QL3 we obtained 57.83 kilowatt, and QL4 we obtained 57.66 kilowatt, and QL5 we got 57.86 kilowatt. So next part is to calculate the rate of heat transfer in condenser. So using the same formula, we can get the heat transfer rate for the Q1 is negative 72.55 kilowatt, and Q2 equals to negative 60.2 kilowatt, Q3 negative 47.82 kilowatt, Q4 we got negative 35.83 kilowatt, and Q5 we got negative 23.85 kilowatt. So the next question is to explain the effects of changing the condenser flow rate of T1 to T5 to compressor power. Draw the graph and discuss the results obtained. So from here we can see the graph. So at the list of condenser flow rate, which is 10 gram per second as the lowest compressor power, and at the highest condenser flow rate, which is 30 gram per second as the highest compressor power. So from this graph we can conclude that the higher the condenser flow rate is the higher the compressor power. So next I will continue with the conclusion. As a conclusion for this experiment, the coefficient of performance is directly proportional to the rate of heat transfer of evaporator. It follows that the condenser flow rate is proportional to the compression force. On the other terms, as the condenser flow rate increases, so does the work input. Last but not least, it can be said that the flow rate of the condenser is inversely proportional to the temperature. So that's all from us. Thank you.